So now we're going to look at the potential from a continuous charge and basically it's just this equation right here. So if I want to calculate the potential at this point, and for example, this might be like a volume charge, then I need to sum all the contributions. And if I make this to be really, really small, then the summation of all these contributions become an integral, so you can approximate that to an integral. That's given by this equation. So with this, let me take a moment here. I want to go back and share my screen, because I think if you understand. So I'm going to make a table here that is going to help explain. So let's look at electric potential here. So electric field. Let's say the source. Let me just want to add a source here. So source. I'll just write this as electric field. Electric field. Remember that electric field is the Newton per Coulomb. Electric potential. It's my joule per Coulomb. Now I want to make a table here. And so in this table here, let's look at the source. So when the source is the point charge, when the source is the point charge, the electric field is just equals to, remember that this is a vector? It's KE Q divided by R squared times the unit vector in that direction. The potential has nothing to do with vectors, it's just a number, so the potential at that point is just KE Q over R. What if I have several point charges, not just one, but several point charges. Then in this case, I calculate my electric field using this equation here. I think you should remember this from, so this is KE, the sum over I. So for example, I would take 1 to n. Qi divided by Ri squared. So Qi divided by Ri squared, and then multiplied by the, so for example, it means that you need to take all the source charges, you calculate the unit vectors and everything, and then you do that summation. Now for electric potential, again, I don't need to take any vectors, but you just sum is Ke, the sum from I equals to 1 to n Qi divided by Ri. Then finally, what happens when you have a continuous charge? For a continuous charge, the electric field is equal to KE integral of dq divided by r squared. Now remember that dq could be equals to lambda dx, dq equals to sigma dA, dq could be equals to rho dV. So it depends. Am I talking about a line charge or a surface charge or a volume charge? Then for the potential here is the same type of, so this is just the KE, the integral of dq divided by r. Again, dq could be a line charge. So this could be a line, could be area, surface charge, or volume charge. Let's see. So with this, I want to look at one example here. But let's suppose that are you guys done with this? So with this, I want to look at one example. So so suppose that you have a line charge that looks like this. This is the point 0, this is negative delta 2. This is delta 2. I want to calculate the potential at point P such that the distance from here to here is A. Then remember that this is a continuous charge. So because this is a continuous charge, this is the equation that I need to use. So this is KE, the integral of dq divided by r. So again, just as we did for electric field, I need to set up this integral. Then once I set up this integral, I can use my table of integrals to find that value, right? But I need to know what is my dq and what is my r. So let's go ahead and do something like this. So I'm going to cut a small area here, small length. And then we'll call this dx, such that the distance from here to here is x. Then the distance from my dx to that point is r. So do you see that r is going to be equals to, does everyone agree with this? That my r is the distance from my dx vector, that small length, to that point that I'm interested in, is given by that equation right there. So now we know what r is. What is my dq? Because this is a line charge, my dq is equals to lambda dx. Again, remember that this lambda is the total amount of charge that I have per unit length. And so now the next thing is just to take everything and plug it into that formula right there. So I can go ahead and write this as my V is equals to KE. Now in place for lambda, I'm just going to put Q over L, so KE Q over L. The integral from negative L over 2 to L over 2 dx over x squared. So you see that this part. So this integral from negative L over 2 so we can calculate this from table. So I don't have my table of integrals here, but I don't know, does anyone have that okay, yeah, I do. So let's see if we can find this integral. Okay, it's not here, but I think there was one formula sheet that I sent to the class on D2L that has this that integral in it. But again, this will just come from a table. So I'll leave it like this. Then maybe we can substitute that value once we have that value for the integral. But I think the main point is just to understand how to set up the integral, So as an example, what if we want to solve the same problem, but now what if my point P is right here? And again, that distance is A. So if my point P is right there, I can do pretty much the same thing. So you say this is my dx here, and the distance from here to here is x. The distance from here to here is my r. So if you do it correctly, I'll just write the final result here. You should get Ka Q over L. In this case, you're going to integrate from 0 to L dx over the square root of x squared. The only difference here is that I'm doing the integral from 0 to L, not from negative L to L. Does that make, do you guys see the difference? So when to use negative L to plus L and when to use 0 to L just depends on where I'm calculating my. So this is going to be in the drill tomorrow. So you have this in the drill. So I'll give you this just to practice. But basically it's just to set up the integral. Then use your table to look up the value.
And since it's doing like potential difference, there's no direction.
There is no direction, right? Yeah. So this is, it's just like, so no direction. It's a scalar quantity.